All right, so on this one, so they're giving me the equation y equals x plus 1. So I'll graph that. So it's a y-intercept of 1, rise and run of up 1 over 1. So there's that line, and then they say y equals 1. So y equals 1 is going to be that line. And then they tell me x equals 8, which is going to be that line. Is that okay? Alright, so I cleared in. So x plus 1, so it's a y-intercept of 1, and then a rise and run of up 1 over 1, right? Okay. Then if y equals 1, that's when it says y equals, that's telling you the axis that your line is going to pass through and at what value. So it's going to pass through the y-axis at a value of 1. So that's going to be that line right there. And based on another way of thinking about that is that it says y is 1. Would you guys agree that no matter what order I pick off that yellow line, the y value is 1? And so that's what they're telling you when they write y equals 1. When they say x equals 8, they're doing the same thing, but they're telling you what the x value has to be. And the y value then can take on any value that it wants. So x equals 8 would be that that vertical line. So the plus 1 tells me my y-intercept, and then the slope is the coefficient in front of x, and that's 1, so it's 1 over 1, so up 1, right 1. So then it asks you to find the area of that, yes? Eventually? Okay. So what kind of triangle is this if I just used a horizontal line and a vertical line? So it's a right triangle. So can I use this as my base? So that distance right there would be 8, right? That's my base. Can I use this distance as my altitude? So how long would that distance be? If I go from 1 up to 9, that's got to be 8 as well, doesn't it? Okay, because I'm starting at 1. So then that would be, so a base of 8, an altitude of 8, so 1/2 times 8 times 8 should give me 32 square units. Which means to us, obviously, hopefully we understand this, but that means that 32 of these little squares right here, 32 complete individual squares right there, can be redistributed and placed on the inside of this blue triangle. And that's the concept of what area means in regards to square units. Does that help? Any others? Yes. And is this the one you were talking about, Jagger? Well, yours is going to be the same as mine. So the thought here is that this is a composite, I keep saying function because we're talking about composite functions in another one of my courses. This is a composite figure. I don't even know what you call that. Okay, it's got 1, 2, 3, 4. It's a pentagon. Okay, concave pentagon, irregular pentagon. We don't have any formula for it. Okay, so you have to break it up into whatever portions that you think would be manageable. Okay, I can see 2 that would be useful. I can see 1 that really simplifies things. Okay. So if I do that, then I know that this rectangle is going to be 140 times 50, right? That's going to be the area of that rectangle. Then this triangle, now because of the way I structured this, if this is a parallelogram or a quadrilateral with 3 right angles, it's actually a quadrilateral with 4 right angles. So this has to be a right triangle, which is nice because now this here would be maybe H, and maybe that's B. Now, because of the right triangle, those could switch, but I got to find those distances. How far is that distance right there? Or how long is that distance? 50. So what does that make this distance here? 110. That's just a segment addition postulate. And then, same logic, if this distance here is 60, that means this purple distance here has got to be what? It's got to be 80, right? Okay, it's got to be if the whole thing adds up to this side of 140, we know 60. That's going to be 80. So H equals 80. So I could go area of the rectangle would be 50 times 140, and then the area of the triangle would be 1/2 of 110 times 80. And then what do I do with those two values once I realize what they are? Add them together. Is that the only way? No. The other technique that I see people commonly use on this question is to draw this over. So you got this little rectangle here, right? Now maybe after today, this will be manageable as two objects, two shapes. This is a rectangle, this would be a parallelogram. But right now, we don't know a formula for a trapezoid. So the other thing that you would do here is have that, right? So now you got these two rectangles, right? But regardless, you still, no matter how you approach this, you still have to draw that line right there. So it just makes sense not even to worry about that one. So we're okay with that? Does that make more sense now? Okay. Anything else? Yep, we do that one in class. That's one of the examples. So what do you know about a rhombus? All sides are the same. Diagonals do what? Diagonals are perpendicular. What else about diagonals? They bisect each other, okay? So if that's 9, this is 9. If that's 15, this is 15. I'm just going to draw one of those triangles. You know 9 and you know 15, right? Will that allow you to solve for, let's call it A, that distance right there? Using what? Pythagorean right there. So I say 81 plus A squared equals 225. A squared then will be turned into 144. What's A got to be? 12. If A is 12, okay, so now that's a right triangle now, right? What number would you use if I want to find the area of that triangle? 12 and 9 are going to be your base and your altitude. And they can flip-flop, doesn't matter which one's which. So that gives me 6 times 9, which is what, 54? Now, how many of those triangles do you have in your rhombus? You have 4. So multiply this by 4. So it gives me 116. Sorry, 216. Is that okay? We will have a formula for a rhombus at some juncture, but right now we don't, so we have to rely on properties that we know to be true that breaks a rhombus down into triangles. So we can access then a formula that we do know for area. Trapezoids. Trapezoids. Let's derive the formula for the area of a trapezoid. So I created this applet here to help realize visually what we can do with a trapezoid and how we can use our rectangle formula to generate a trapezoid formula. Okay? So what I'm going to argue to you when we're done with this is that if you know the trapezoid, or if you know the area formula for a rectangle, base times height, right? Then you should know the area formula for a trapezoid, or maybe get to the point of that. Okay. What I always struggle, and I think I've told you this before, I don't want to give you a formula because the formula is pretty nasty. I don't want to give this to you, which is area equals 1/2 HB1 plus B2. It's kind of a messy formula. You've probably seen it before, maybe in 9th or 8th grade. I don't want to give that to you and say, hey, that's just a formula, just plug things in and it works. Okay? I want you to see why it works. All right? That's I think a very important thing that in a lot of math and science classes gets overlooked and then leaves people in the dark with formulas. In order to do this, we need to understand what a altitude is for a trapezoid. It's the same as it is for a parallelogram. It's going to start at one of your parallel sides and then go perpendicular to the other. So if I click on altitude, those are altitudes, okay, for a trapezoid. Now you can also, I think the way I said this, I haven't messed with this for a while. Any other segment that would be in here, like that one there, as long as it's perpendicular, and it's perpendicular to this side, it's going to have to be perpendicular to that side because the top and the bottom are parallel. So they have to be same side interior angles, they have to be supplementary. One's 90, they're both 90. So those are all altitudes of a trapezoid. Are you okay with that? Now the reason I choose these two that are dotted there is because they take our trapezoid and they break it up into a triangle, a rectangle, and then another triangle, right? And now these triangles down here, they don't have to be the same, okay? And I can actually work with, now this would be kind of a bizarre trapezoid, but still a trapezoid, okay? We can have a right trapezoid as well, okay? So we can do all these things, but I want to show you with this, and if we can show it with this one, then it's going to be true for all of them, okay? All right, so what I'm going to do is I'm going to find the midpoints of the legs of the trapezoid. So the legs are going to be the segments that are not parallel. Okay, so segments that are not parallel are my legs. There we go. I want to make it a little bit bigger. So I'm going to find the midpoints. Okay. Now what I'm going to do is I'm going to find that segment right there. Okay, and I'll actually remove the altitudes real quick to look at that. And we addressed this previously in I forget what chapter it was, but if I gave you these points, so let's say that, and I'm not going to go through all of the algebra here, but if I say at this point here is like 0, 0, let's say at this one is like A, B, let's say this one is C, D, this one is E, actually this one would be, we'll have to fix this a little bit, E, D, because they're going to be, let's say that is parallel, or these points A and B are horizontal one another. Let's make this point A, 0, so these are the same. What we can do is we can find that midpoint, which would be the average of these x's, the average of these y's. I can find that midpoint, which would be the average of these x's and the average of those y's. And then once I find those two midpoints, I can go through the distance formula, which will be, the x2 minus x1 squared plus y2 minus y1 squared stuff with this new ordered pair and that ordered pair. Okay? And what that will eventually do for me is it will provide me this formula. Okay? I got to do a little bit more. I got to do the distance formula here and here as well. But the distance formula will generate 1/2 b1 plus b2. Okay. If we have time, maybe later on, I will go through that process. But that is true. You guys remember talking about? I think what we really did is we did it with. Specifically, we did it with triangle. We found the mid-segment of a triangle, and actually, we did walk through that proof and found that distance would be 1/2 the side that the triangle, that the mid-segment was parallel to it. If it's a trapezoid, it's 1/2 the sum of the sides. Okay, so I'm going to tell you that is true, but we have the ability to go through and find that distance. Is that okay with everybody? So what I'm going to do here, what I want you guys to see is where does the formula 1/2 HB1 plus B2 come into play? Well, what happens if I have my mid-segment there, I have my altitudes there, okay? What we're going to do is I'm going to take this altitude here, and I'm going to slide it out so that it's right there, okay? I'm going to take this altitude, and I'm going to slide it out so that's right there. They're parallel, okay? And I just wanted to make them so they pass through the midpoint of those legs. Is that all right? Now what I'm going to do, you can see hopefully what that does. Because this is a right angle here, when I move my altitude out here, it's still a right angle, right? Okay, so let's just kind of ignore this. So these are still my altitudes. These are perfectly fine altitudes to put in anywhere we want it to. I'm going to take those triangles right there that are created. I'm going to rotate that one to right there. I'm just going to displace that area. Does that make sense? Okay. And then I'm going to take this one and rotate it right there. Okay. Now, I wish this would have disappeared. It won't even let me hide it. But now do you see this rectangle right here that just colored all in green show up? Okay. Well, the side of that rectangle now is this altitude that we moved from the inside out to there, right? And now would you guys agree that this distance right here of my rectangle, the other side of my rectangle, is equivalent to that mid-segment of our trapezoid? So this distance here is 1/2 B1 plus B2. This distance here is H. So if I multiply those together, I get the area of this green rectangle. Well, the area of that green rectangle was found by looking at that area there. I just repositioned it, right? Does that make sense, everybody? So when we talk about our formula for the area of a trapezoid as being 1/2 HB1 plus B2, it's because that is, after reconfiguring and moving areas around, we can make a rectangle and use B times H to find this formula. Does that make sense? And all your formulas have some type of underlying procedure or concept like that behind them. Okay? We'll get into it. Hopefully we have time. We'll talk about spheres. Okay? We'll try to find the volume of a sphere. Okay? So the volume of like a ball or whatever. Do anybody know what, and this is kind of weird, the volume of, I'm assuming we probably don't know this, the volume of a ball or a sphere comes from knowing the volume of a pyramid. Okay? Which is very, very bizarre that that's the case. Okay? But the volume of a pyramid, if we think about it, we draw a lot of connections all the way back, comes from the area formula of a rectangle. Okay, so our rectangle is the kind of the driving force for a lot of the things that we talk about in regards to these formulas. Okay, 1/2 HB1 plus B2, and H has to be the altitude between the two bases. Okay, B1 plus B2 is the sum of the bases. Okay, and it does not matter which one is B1 and which one is B2. All right. I think we can go to a little bit more complex question down here instead of that story problem, that picture problem with Nevada. Right here, I want to find the area of this thing, and I probably did a bad job. I probably should have a right angle here Okay, but this is just an irregular trapezoid. We don't know if it's isosceles. We don't know if the legs are the same. It looks like the legs are different. If it's isosceles, the nice thing is that the triangles that are created are congruent. But if I draw, this 7 exists right there as well, my hope is that you can argue that triangle number 1 and triangle number 2 are probably different, right? Okay. Now, so if I go through and I figure this out, what value up there is your altitude? 7. That's H. So what I like to do a lot of times is I like to write my formula down. And I just start listing the objects that I need. Okay, I need H. I got that. I need B1. Do I have a B1 here? Do I have a base that I know the value of, the complete value of? Isn't this a base? Now that could be B1 or B2, but it's one of them. I know the complete thing. But do I know the other base? Do I know that complete distance right there? No, not directly. So that's unknown. So that's where I'm going to go. That's I'm going to draw my attention down to that base and see if I can figure out what it is. What kind of triangle is that? It's a right triangle. So if you know two sides of it, you can do Pythagorean theorem. So I can say 7 squared plus, I'll call it A. Just call this distance here A. So we're talking about there, all the way through there. So we get 7 squared plus A squared is equal to 11 squared, right? That's 49 and 121. So A ends up being, what is that? So 120 minus 50 would be 70. So this would be 72, wouldn't it? Is that right? So A squared is 72. So then A would be radical 72, right? Okay. What perfect square hopefully jumps out at you when you see 72? Divide 72 by 2. What do you get? What's 72 divided by 2? 36. Is that perfect square? So this is actually radical 36 times radical 2, which turns into radical 6. 6 radical 2. So that's the length of A here, 6 radical 2. Is that all right with everybody? So what is the length of this base down here then? What is this second base's length? It's that plus that, right? Can I do that? So my question, and this is where I would use a tool like Desmos. If I think, so I know that distance, because of the segment addition, is 6 radical 2 plus 13. Does anybody debate that? That's how I'd find that distance. I would walk 6 radical 2 units, and then walk 13 units, and I'd add those together to see how far I walked total, right? So the question is that the same thing as then 19 radical 2? Because what you did is you added the 6 and the 13, right? Are those two values the same? No. So is the rule of adding the numbers there and there, is that a valid rule? No. Okay. What we find out, and what we hopefully realize, is that those cannot add together. We can't. We're going to leave it as 13 plus 6 radical 2. Okay. For the mere fact, the reason we can merge things together would be something. I'm just going to draw a comparison over here to something a little bit different. Let's say I had like 3 radical 2 plus 5 radical 2. What do both those things have in common? Radical 2. So I could do this. I could factor out or divide out a radical 2 of this and divide a radical 2 out of that, right? Would that leave me a 3 plus 5 here? Does that make sense? What's 3 plus 5? It'd be 8. So now I can rewrite that as 8 radical 2, correct? And that hopefully gets us to see that, well, how can I get that 8 quicker than doing what we just did? Take that 3 and that 5, right? If I look at 13 and 6 radical 2, there is no common factor that can be divided out so that we can then add things together like we added the 3 and the 5. Okay? So it stays 13 plus 6 radical 2. Is that doable? All right. You're only going to add or combine radicals if you have the same radicand. Okay, if that radical 2 is consistent. So now we got everything. Now we just got to plug it into our formula. So area equals 1/2 h, which we said was 7, plus the sum of our bases. Well, one base was 8, and the other base was 13 plus 6 radical 2. Is that okay with everybody? Okay, so now it just becomes a practice of how they ask us to answer the question. Do they want it in a decimal? Do they want it rounded to a tenths place or a thousandths place or whatever? If that is the case, I'm just going to go to Desmos, TI, whatever I'm going to use, and I'm going to type this thing in directly the way I wrote it. And I get that number there. Okay? Now, if they want it in a simplified version, then I got to do a little bit of work here. Okay? First thing I would do is go look through and find combined like terms. See if there's anything that's similar. Can I add those together? So I'll have 1/2 times 7 times 21. Sorry, 20. It is 21. I don't know. 21 plus 6 radical 2. Okay. Now I have to decide. I've got 3 things. Which ones I'm going to multiply together first. Just because of just thinking ahead, I think these would probably be the easiest ones to multiply together. What's 1/2 times 7? Okay, 3.5. But because I want to go exact values, I'm probably going to leave it as just 7 over 2. Now 3.5 is exact, but a lot of times we just leave that as 7/2, because I know the next step is to multiply here. Okay, so now if I multiply here, I need to distribute that through, right? What's 7/2 times 21? What's 7 times 21? 147. And then the 2 times the 1 gives me 2. Okay. 7 times 6. What's 7 times 6? 42. And then I got the 2 times the 1 there, so 2 on the bottom. And then I'll have my radical 2. So I get here 147. I can write this a couple different ways. 147 plus 42 radical 2 all over 2, if I want to write it that way. Or 147 over 2. That does not reduce. That's an odd number. Plus then, now, this would reduce. So I can write that as 21 radical 2. So either one of those versions, that one or that one, would be acceptable as a simplified answer that is exact, right? If I type it in this way, that's exact right there, but it's just not simplified. But we should be able to see, and this is what I would do, because in the past I've had people struggle with the algebra that exists here. Okay, my hope is that we build some confidence with that, because that's going to be algebra that is not out of the ordinary when you get to algebra 2, when you get to college algebra, trigonometry, stats, calculus, integrated 3, whatever route you go. Okay, any math course that you take beyond this one is going to ask you to do this kind of thing. So I already know that this is going to be the answer. Let's see if those other options have been evaluated correctly. They're the same. And then I can see that 147 over 2 plus 21 radical 2 would also be an option. Okay? So those two formats will be eventually things that I ask of you. Math Excel might jump back and forth between, write it as a decimal, rounded or something like that. Okay. What I always do, no matter what the problem asks, if you take this approach, it's not only going to always get you the right answer, but it's going to build your algebra skills. And I think a lot of our geometry problems, and really all the problems that we do throughout every math class that is not focused directly on algebra, a byproduct is that your algebra skills get refined. And that's usually what the thing that people struggle with in stats, what they struggle in calculus, what they struggle with in my trig class is the algebra. It's not the concepts that are in those courses. So if you force yourself to do things like this, where if they want it rounded to a 10th place or a 100th place or a 1000th place, don't just go straight to the calculator. Find the exact answer first. Make yourself work to that. And if I got the exact answer, then I'll go to the calculator, type the exact answer in, and now no matter what decimal point I want, I'm accurate to. Does that make sense? Okay. Byproduct of that is that you become much more refined with your algebra skills. And then obviously the better you are at algebra, the better you are at all of your math. Give that one a shot. Let's give it some time on your own. Just think about what you can do with that one to find the area. All right, so in this one, area, again, start with your formula, 1/2 h b1 plus b2. All right, so what's b1? Okay, 5. It's fine. What's b2 then? I do? When they say, isn't that B2? Because they don't, and this is something that I think people get confused with because you just have to understand the way that they present images. Like if they didn't want the whole thing to be 7, maybe they only wanted, so I'm going to draw my altitude in here eventually. If they only wanted that to be 7, they would have to put those bars in. Does that make sense? So if they don't do that, the assumption is that the entire distance that is beside is 7. So that whole base 2 is 7. Now, does it really matter which one's B1 plus B, or which one's B1, which one's B2? No, and the reason it doesn't matter is because addition in my formula is commutative. Okay? So I've got those two things. I just don't have H, right? And this is where this is different than what you might have seen in previous courses. In previous courses, you probably saw that formula. May have seen. Has anybody seen that formula before? Okay, you're going to see formulas that we come across in the remaining days of this course that you have seen before. But in those courses where you saw them already, they would just hand you. They would give you all the values that you need. It'd be very obvious what H is. It'd be very obvious what B1 and B2 are. It would be explicit. Here, they are implying what H is. They're not telling you, but they give you enough to find it. If I draw this down right here, I could use SOHCAHTOA, okay? But generally with a question like this, because of the angles they gave you, they're going to ask you to find the exact area, okay? Which means SOHCAHTOA is probably not the route that you want to go. If I do this, what kind of triangle did we just create here? A 30, 60, 90. You have a special right triangle here. Okay? Now, in order to work with a special right triangle, I need to know some distances. Okay, we know if this is 2n, this is n radical 3, and this distance here is n. Of those, do I know any of those values? I know n. I know n is what? N is 2. Okay? Because this shape, the way we structured this is a right angle. We drew this down. That's a right angle. That must mean that that's parallel to that. That's parallel to that by definition of a trapezoid. Therefore, we now know that this 5 can transfer down to this segment right here. leaving me a distance of 2 right there. So what is this distance right here going to be then? 2 radical 3, and that's h, right? So I go 1/2, 2 radical 3, and then what, 5 plus 7 was 12, correct? Right, if I multiply all those together. So right now, really, and then I've got, how many numbers up there am I multiplying together? This might be a trick question, the way I've got things grouped. Is 1/2 a number? Yeah, it is. Is 2 radical 3 a number? It's a product of 2 numbers, isn't it? Okay, when I write it this way, that's the product of the number 2 and the product of radical 3. And then 12 is a number. So there's actually 4 numbers here being multiplied together, right? Does that make sense to everybody? I'm going to do that. You don't normally have to do this. You could do this in your head. But of those 4 numbers that are being multiplied together, are there a group that are like objects, like numbers, come from the same system, or not the same system, but same set, same group? 2 and 12, they are rational numbers, right? 1/2 is also rational. I'm going to look at this. I'm going to group these. 1/2 times 2 times 12. Those all come from the same group of numbers. Okay, if I show you, let's see here. All right, so this is our Venn diagram of our real number line. Okay, 1/2, 2, and 12 all come from this group right here. Okay, they are rational numbers. Radical 3 comes from this group. Okay, and what we find out, and it's at a higher level of algebra, but what we find out is that when I take rational numbers and I start adding them, multiplying them, I get other rational numbers. Does that make sense? Okay. And that means that group is what we call it's called abstract algebra. We call it a closed set. Okay, meaning that when I take something from the group and multiply it, take 2 things from that group and multiply it, it gets me something else in that group. Okay, so it's a closed set. So what we want to do is look at those as a product of values. And we're going to 1/2 times 2 is obviously 1, then times 12 is 12. So that's my rational value, and then I still have this radical 3, which is irrational. So I'm going to write my answer that way. I'm just trying to demonstrate there, when you have a product of a series of values, and some of them are rational, some of them are irrational, generally the practice for us in algebra is to take and use the commutative and associative properties of addition and multiplication and group your rational values, and then do the work with the rational values. Then group, if you have multiple irrational values, do the same thing with the irrational. And at the end, when you present your answer, something like this, where it's a product now of the rational and irrational. I'm not telling you what 12 radical 3 is as an exact value, right? Or, sorry, as a value that you know off the number line. You can't, if I gave you 12 radical 3 in a number line, I say go put 12 radical 3 up there on the number line, are we going to be very successful at that? No, probably not, okay? Now, it's less than 24. How do I know it's less than 24? What would 12 radical 4 be? Wouldn't 12 radical 4 be 24? Because radical 4 is 2, so 12 times 2 would give me 24. So 12 radical 3. Radical 3 has got to be then less than 2. So 12 times radical. So radical 3 is about 1.7. So 12 times 1.7 will be less than 24. So I knew it was going to be bigger than 12, but less than 24. But other than that, I'll probably be closer to 24, but I'm not going to be very accurate in putting that on the number line. But that is the exact value of our area. And if I needed to change it to a decimal, then I could grab my calculator and put it in as a decimal. Does that make sense? Okay. Again, the geometry, I'm not a big stickler on spending a whole lot of time on the geometry, because if I give you a formula, everybody can take and plug the values into the formula. What is B1 in this case? 8. What is B2? 14. So you've done this substitution process forever, right? This should be a distance that we know. We should be able to come up with that based on the experience and the time that we spent already in Chapter 8. If this was 8 right here, that's got to be 8 as well, so this is 6. And in a special right triangle, that's 45, 45, 90. What is that distance? 6. So we should be able to find all those things, right? Okay. And my hope is that we've already geometrically spent time and developed the skills to do that. What I like to spend time on, because I think it's something that we're very rusty on collectively. Now, I'm not just saying you 15. It just, even myself, there's algebra I can get better at, okay? Just collectively in the last 14 years of teaching math, I know that this is always something that people struggle with, okay? So I like to talk about that algebra because it'll make your lives easier when you get to my other courses, okay? So I got 1/2 times 6 times, then this is going to turn into, what, 22? So that's going to be 66. And be square millimeters, right? All right. So this makes sense, areas of trapezoids? Okay, you might have to do some legwork to find distances. You have to rely on segment addition. You have to rely on SOHCAHTOA. You have to rely on special right triangles. A lot of times they don't always give you the best directions on how they want an answer to be written. A thing that you can assume, though, most time, if they use 60, 30, or 45 in the problem as an angle, they are going to want answers left with radicals in them, and they want simplified radicals. Okay, if that angle there would have been 38 degrees, I have to use SOHCAHTOA, and when I use SOHCAHTOA, I have to use my calculator, and chances are they're going to be okay around it to 1 decimal place, 2 decimal places, whatever. So the components that they provide you with to start with might lead you to how they want the answer to be written. Okay, so look for those 30, 45, and 60 measurements, and that will lead you to using exact values. All right, tomorrow we're going to talk about some of that stuff again. We'll answer any questions you might have, but then we'll get into talking about the formulas for kites and rhombi.